Our lecture today is about unsymmetric bending. It is something that you, as engineers, might face in your work life. Might be possible if you go in the direction of, for example, structural design, construction, or even some specifics of maintenance engineering or something like that. You might be facing with such problems that require dealing with unsymmetric bending. And let me search on the internet. I believe it would be a nice touch if we get a real example of what an unsymmetric bending looks like. Let me see. L-shaped beam in cantilever. Let me see if I can find some real image, something that is an application. This tends to be difficult or what? Let me see here. Structure. Unsymmetric bending. Yeah. Well, I guess it's difficult to find such a picture. Pratt. Truss. Just bear with me a few seconds more, because I'm trying to find a very good picture to show that. Should have looked for it beforehand. No, I cannot find any. Well, let's not waste more time. All right, so let's put it in this way. What you have learned so far related to bending is kind of covered under the umbrella or of something called simple bending theory or Euler-Bernoulli theory. Yeah? And the way you could use those concepts to determine bending, not only to say how much is the stress or the maximum stress you're going to find in such application or structure, but only to find the deformation of it, because remember that the things we have dealt with in this course is related to failure, but we looked at failure from two perspectives. So we look at failure from the perspective that's going to break or not, or the perspective of that's going to be deformed so much that we cannot use it anyway. So 2 points of view. And those points of view apply most basically to ductile materials, steels that we're using here. So simple bending, the theory of simple bending is something that I could write it, that stress is found on simple bending is the moment times the fiber or the distance from the neutral axis to the farthest away point, let's see, then divided by the moment of inertia. This is a formula you already know. Then that's going to give you a value of stress. Yeah. And again, that's applicable to only simple bending. But then you should ask the question, okay, but what is simple bending then? So how do I know some simple bending from some complex bending? Something like, is that the name? And let me write it down right here. So this corresponds to, maybe blue, simple bending. Good. So what is simple bending then? So let's define simple bending. So then whatever the other case that does not fall in that definition that we're giving right now, then it's not simple bending, it's something else. So let's look at the first picture here, this one here. First picture with one. So it says that simple bending is somehow of, say, situation happening in elements or in these kind of elements. So when, for example, a moment or a force causing a bending moment makes the element deform, yeah, on a plane which is a plane of symmetry. So if you see in this picture, you have the word or the phrase plane of symmetry. And then if, for example, these forces F1, F2, and F3, those forces are going to cause a moment which axis is perpendicular to the plane of symmetry. So I'm going to draw it like this. So this is perpendicular to the plane of symmetry, sorry. then that deformation is going to occur as such, something like here in figure 2. Yeah. So when that happens, when the deformation occurs in the plane of symmetry, then we're talking about simple bending. And if we're talking about this simple bending, we can apply this formula that we have written here. Here in figure 3, this one here, you see, for example, we have a square or rectangular section. So the difference between picture 3 and pictures 1 and 2 is that in picture 3, we can assume, or we can say that there exists 2 planes of symmetry because we're talking about a rectangular section. So if I draw that section here, maybe green. So if I draw this section here, then we are talking about a couple of planes of symmetry. So we're talking about this plane of symmetry here. So, and then we're talking about this plane of symmetry here. So it has 2 planes of symmetry. Then pictures 1 and 2 are describing a profile with a section that has just 1 plane of symmetry. So if I draw that section here also, so we're going to have this kind of a trapezoidal section, something like this, and then like this. Yeah. So my planes of symmetry. So I'm going to have just 1 plane of symmetry, this one here. But then there is not going to be another plane of symmetry, so just 1. So simple bending definition is like that. It's a deformation that occurs on a plane, or is a bending that takes place on a plane of symmetry, or about an axis that is perpendicular to a plane of symmetry, more correctly said. What questions do you have so far? None. Okay. So, and this is the concept that I'm going to introduce here, and I believe it's the message that I want you to take home after you finish the lecture, because we're going to be working around this only concept, and the concept is about moments of second moments of area, or product second moments of area. Okay, but before that, so now that we have defined what is simple bending, then whatever does not fall into this case, then we are talking about something else than simple bending, and we are going to call it unsymmetric bending. Write that down here. Trick bending. Good. And unsymmetric bending, then, when we talk about planes of symmetry, we are implicitly speaking about moments of area and moments of inertia. So they're very different from those. So we're talking about kind of one specific concept or 2 specific concepts that are second moments of inertia, of area, sorry. And what is the product second moment of area? Just 2 concepts. Because these concepts describe let's say the inertia of the elements, and the inertia of the elements are some sort of description of the geometry of it. Yeah. And just to bring the formula, I'm going to write down here that, for example, a moment of inertia, or the moment of inertia that is defined by the second order of the second moment of area, so it's going to be defined, for example, about an axis, to call it x. It's going to be the integral of this term here around the y-axis, moment of inertia. So this is also information you already know. And then the product second moment of area, or the product of inertia, is going to be this one here. Perfect. And let's look at first more sections, because I have more sections here, more figures here. So for example, if we talk about, okay, what are symmetric sections, what are unsymmetrical sections? So these ones here, represented by this part here, well, intuitively, we know that these are symmetric sections because you have 2 clear axes that they divide the part or the section into a mirror parts, let's put it in that way. And then unsymmetric sections, you have these ones here, because those 2 axes defined or drawn there do not divide the parts into mirror parts. Yeah. And then you have this one in the middle. which only has one plane of symmetry, which is the vertical one, and then you have the horizontal one that is, well, this is another axis, but it is not a plane of symmetry. Yeah? Then one of the things with symmetric sections is that symmetric section, or the planes of symmetry of symmetric sections, are equivalent to those maximum, let's put it, how to say it, are the maximum principal axis, or they're called principal axis on the whole geometric definition of what we're describing here. Yeah. So you have axis of symmetry, and you have principal axis. Yeah. So those axes of symmetry, when we're talking about symmetric sections, are equal to the principal axis. And the principal axes are those, let's say, axes where the inertias that you, or the second moments of area that you calculate, are maximum and minimums. But in the non-symmetrical sections, what you have is that those what are described there might be the, are just, some axes, but no, the principal axes do not coincide with the axis of symmetry. Yeah. And why this is important? Because when we talk about bending considers that the bending is occurring about an axis about a principal axis. Now, if we are facing, or we're talking about unsymmetrical sections, then we cannot use simple bending, the simple bending formula, because it doesn't apply there. Means that we need to find a way to, if I tell you, well, this is an unsymmetrical section, these are, let's say, some axes that I'm using for my construction, for my structure, but they are not the principal axis of symmetry, or principal axis, sorry, then it means that I would need to find a way to calculate how are oriented those principal axis, so I can use the simple bending theory after I have gotten those values, or those orientations. Because we don't have a formula specific for unsymmetrical sections, so we are just bringing the unsymmetrical section and somehow making it some sort of symmetrical equivalent section to be able to apply the simple bending. So this is an important concept. And why is that? Why would I like to bring or to calculate those symmetrical, or those principal axes? Yeah. So let's look at this figure also that I extracted from a book, I don't recall, or from internet. And for example, these two first profiles or beams, in this case, for example, this is an I or H beam. Well, it's logical that they are bisymmetrical, meaning that these Y and Z axes are symmetry axes, and which means, well, in this case, they are symmetric sections. And if they are symmetric sections, then it means that these symmetrical axes are coincident with the principal axis of symmetry, principal axis. Then we know how the stresses are distributed around it. Yeah. Also, in this case, for the case of the U channel here, is the same. But for these symmetrical and unsymmetrical sections, like this Z type or this L shape, using, for example, these same axes that I'm presenting here is not going to give me the correct information, meaning that I could not use this simple bending theory. So I would have to find an orientation of this axis of the section, so the distribution of my stresses are uniform, from each one side, on the top or on the bottom. The same kind here. So that's why I need to find this principal axis. And also, if the section is so irregular, so I not only need to find what is the orientation of the principal axis, but I need to find also how the neutral axis is located, because if I want to move the analysis forward from the stress part to the deformation part, I know that in a bending situation, bending occurs around or about the neutral axis. So I not only need to find the orientation of the principal axis, but I need to find the orientation of the principal axis, of the neutral axis, which can be way different than the orientation of the principal axis. So things might get complicated, but just from the talking point of view, because from the application, from the development of the whole equations that we need to take into account here, is a completely different situation. Now let's take this case in here. By the way, this is a very good question for the exam. Yeah. Kind of what is unsymmetric bending? Defined from the point of view of principal axis and symmetry. Yeah. So take notes about this one. So now the question is, so what about, before I jump into this figure here, So what about if we have a very weird shaped area or section? So what's the definition for a principal axis? Well, long story short, so the definition for a principal axis is that are those axes that you find where the product of inertia, where the product second moment of area is zero, or this product of inertia. So whenever orientation or whatever orientation you find where the term product second of moment of area is equal to zero, then you're in the presence of a principal axis. Yeah? So this is something that appear. And the concept that I told you that I want you to take home is that no matter what the section looks like, there is always an orientation of the axis drawn on the section that are going to be principal axis, meaning that you are always going to find a principal axis, no matter the section is. Meaning that no matter how weird the section is that you're using in your construction, that section is going to have principal axis, meaning that you're going to be able to apply this theory that we're talking about right now. And now look at it from the point of view as an engineer. So we as engineers always try to apply or use these kind of elements shown here. For example, in this type of axis, yeah, we always try to apply loads, for example, like this here. Yeah, for example, like this, or loads like this here. In Z channels or L channels, also we try to apply loads like this, also kind of according to this convenient axis that we have here, because it's kind of easier for us. But sometimes it might be possible that the load application is different from those typical axes that we use. And in that case, we are in this present, or we can help ourselves with this figure here. So, for example, in the first case, we have a rectangular section here, and the simplest unsymmetric bending case is that case where the load application is not aligned with the principal axis or the axis of symmetry, in the case of symmetric figure sections. So, for example, you have a moment caused by forces that are not applied along with the axis of symmetry. So that, for example, in this case, moment A here is not aligned with the axis of symmetry U and V, and then that creates a case of unsymmetrical bending. So that's the simplest case that you can find, because what you do then, if you're in the presence of these two cases, for example, this one here and this one here, where you have moments applied on a different direction or are acting on a different axis than the principal axis, then what you do is that you decompose that moment into two parts, meaning you align them with the principal axis, which are similar to the axis of symmetry, because we're talking about symmetric sections. Then you can work your way around that. For example, for cases 1 and 2, I'm going to write it here. For cases 1 and 2, you're going to have that the moment or the stress, because we're going to know stress, is going to be what? Well, if I have a moment MA applied unsymmetrically, yeah, so this stress can be then calculated from the decomposition of that moment MA, which is, well, I'm going to have from the moment MA, I can have a moment MU, and I can have a moment MV. So if I use those two parts here, and this is divided by the inertia, and then this one here, inertia on MP. Then that's the simplest case, because you just put those values there, so you just find the components of that moment A along the symmetry axis U and V, and that's it. So that's the simplest case. A little bit more complicated case or complex case would be this one here. Well, in this case, because they have just one axis of symmetry, and then, well, you could do also the composition of it, but take into account that depending on how you position that element in your construction or your structure, then you might or not be able to apply the bending, simple bending theory. Why is that? Well, for example, if in the case of the T here, the bending is applied, for example, or the moment of bending is applied in this direction, yeah, bending moment, then is this an axis of symmetry? Well, no, this is not an axis of symmetry. And then, for example, well, and what about if it's applied in this direction? Well, this is an axis of symmetry. And well, if I apply it like that, then I could use the simple bending formula. Yeah. But in the horizontal case, it's not. So I need to find ways to get rid of that. Well, let's see. So let's start with this. So what happens when we're in the more complex case? So we need to find a way to calculate the stress. Yeah. Let me bring down this because we're going to be using this a lot. So as a reference. So I'm going to copy them. Maybe here. Because, yeah, these are a good reference to have. Then let's start by the definition of the second moment of area and how to transform that, or how to try to find how are the principal axes oriented with respect to the axis that you're working for. You have let's call it, you have a convenient set of axes, like in this case, you have U and V in the U channel, but then then you have the principal axis. So you want to find the principal axis from that convenient or this convenient set of axes. Yeah. So I'm going to draw here a Cartesian coordinate system. Let me jump down here. Like this. I'm going to draw a arbitrary, general section like this. In that section, we're going to assume that there is a small area like this. This is small differential area, right? And then that there are distances defined. For example, this is the x-axis, this is the y-axis. Then I can have what would be the correct good color to put it? Maybe blue. Yeah. I'm going to have, well, the position of this, of the vertical distance where this differential area is located. Well, I can measure it like this, and this is going to be y, and the horizontal distance is going to be something like this. This is going to be x. Now, this figure here represents, or these formulas for the second moment of area and product second moment of area are defined by this figure here. So we have a definition of the formula we had and this one. But now our task is to define, well, how much is how are the principal axes oriented in case that x and y are not those principal axes. Yeah. So let me draw another thing. So let me bring back again another Cartesian coordinate axis in here. I might need to move this to a different place, but let me draw it here. And then I'm going to draw a different axis, assuming, well, you know what? My principal axes are going to be oriented in this way here. Kind of like this. And then like this. I'm going to try to make it perpendicular. Something like this. So this is going to be U and this is going to be V. Those are my principal axes. And then these are going to be the X and Y, as defined in this figure here. Good. My whole purpose is to try to find how much is this angle here. Starting from the point of view that I know what are the second moments of area or moments of inertia around the X and Y axis. So how do I transfer that to the moments of inertia on U and V? Yeah. So let me bring again the area here. The same area that we have here, but I'm going to make it a little bit bigger. So this is the area. Yeah. And let me bring again the dimensions X and Y. I'm going to have let's put it kind of away here. This is X. And I'm going to have Y measured from here. This one. Perfect. This is something that you already defined because we're just moving from the left picture to the right picture. Great. But now, this particle is this area, or the position of that area, by considering the centroid of that area, is going to have some distances with respect, or in the UV Cartesian coordinate system, and that can be defined. Let me use a different color for that, like this one here. For example, this one here. This measures U. And this one here, perpendicular to it, measures phi. Any questions so far? This is important because this starts building on top of things, and then if you don't have, if you have something that is not, let's say you're not getting something here, it's better to ask now. No? Okay. Good. So let's then try to calculate as kind of as the principal axis are those axes where the product of second moment of area is 0, then it makes sense to start defining that term, this product of inertia, for this case, because if we can find the kind of if we can find the value for that second product second moment of area, equal it to 0, and then maybe we can find an angle that would tell us how it is oriented with respect to the xy Cartesian coordinate system, right? Then let me define here who is this product second moment of area. So UB, well, in this case, or defining that principal axis reference system or form, or the Cartesian coordinate system formed by the principal axis, U and V, is going to be what? It's going to be U times V multiplied by the differential of area. Pretty similar to this one here, but applied to the principal axis Cartesian coordinate system. Good. Now, as I don't know how much is U and I don't know how much is V, well, I could try to define those terms U and V in function of X and Y. So that's one way to do it. So how would be? So how much would be, for example, U? So U would be, we'll try to find a color here. So U would be kind of this distance here, or to here, so to here. So this vector over here, which I could somehow bring myself to walk some certain distance in X in here. Then let me mark it like this. So I could mark this, put it a bit smaller. Okay. So I could mark, for example, I could walk in X direction like this, but I would have to also to meet certain little bit piece that I'm not finding here. So what I can do is I could try to say, okay, what about if I extend this vector up to here? Let me put it just to mark it like this, and I just find some sort of parallel like this to find this triangle, where I know that this angle theta is repeated here, right? Then I would know that if I could use this x distance, yeah, and I multiply that x distance times the cosine of this alpha of this angle theta here, I could find a distance up to here. But then this distance here, it could be covered by this segment of the triangle, here. So meaning that U can be defined as what? Well, as this small piece here, you can mark it in green, this small piece here, which is x cosine of theta plus this small segment here. And that small segment here, or sorry, in here, could be calculated using the y component and the angle theta, saying that, well, now that small piece that's missing there is y times the sine of theta. Any questions? Right. So then how much is V, applying the same logic? Well, V can be defined as what? Well, V can be defined as this small piece here. How to put it? So, well, V is defined here, but that could be what? Well, it could be that if I take this whole segment here, that I can know because I know the y position, so V equals to y sine of theta, and then I subtract this small piece here, this one here. And how can I subtract it? Well, I know that this is going to be equal to what? Well, to the other component formed by x, which is minus x, the sine of theta. Then I got my U and V. Beautiful. let me extract this one from here. So we're going to be using this as a reference. I'm going to move it to here. Yeah. Then this, who is the product second moment of area? This one, u, v. Well, I know that this is equal to this, but well, it's going to be equal to what? To the integral of u times v, and that is going to be equal to what? To this one here. Plus okay, and I have here, this one here is not sine, it's cosine. Because it's this segment here, so it's defined by the cosine of that angle. Then we're going to have here what? Y cosine of theta minus x sine of theta, dA. So we have defined the product second moment of area of the principal axis in terms of the Cartesian coordinate system that we are using as structurally or practically, or in practicality we're using. Good. So let's separate things, or yeah, let's multiply things, separate things. So let's work with these equations. So again, this one here. So if I multiply term to term, so just to linearize everything, or not to linearize it, but to get rid of the parentheses here. So this is going to be this one time, well, I'm going to multiply term by term. So it's going to be xy cosine square of theta. Then let's put the similar first. So this one times this, then this one times this. I have to do that to shortcut things. Well, plus, it's just, anyway, it's going to be the same. Y square sine of theta cosine of theta. Then this times this is going to be minus x square sine of theta cosine of theta. And then this one times this one is going to be minus again x y sine square of theta, and that's going to be multiplied by the differential of area. Good. Then let's try to group some common terms. For example, this one here, and which one else? And this one here. And then we have another similar terms like here and here. So let's write down the first set. So let me write it like this. Integral of what? Actually, if I work with these two, I can get rid of the xy, extract the cosine of square of theta minus the sine square of theta. So I could write something like this. It would be nice to use the same colors. Cosine square of theta minus sine square of theta, and then this one here, this xy dA, plus, and then the term appears like, again, this is outside, sine theta cosine of theta. Yeah, and then that multiplies what? I can split it right away. Something like this. It's going to be the integral of what? Of y square dA minus the integral of x square dA, and close this parenthesis. Good. Now, what we are working here is with something that most probably will be very, say, leading us to working with some trigonometrical identities. So let me bring them right away. Let me trigonometric. No. Identities. So we're going to have first, I believe one of the first that is more common ones, write it down here, cosine of 2 theta equals to what? Well, 2 cosine square of theta minus sine square of theta. This is also equal to this one. Once you get the rhythm of it, you kind of learn it, sine square of theta. And I should move this somewhere else. So this is also 2 times cosine square of theta minus 1. We write another one, so sine of 2 theta equal to 2 times sine of theta cosine of theta. This is something that we have here. This is something that we have here also. Then we have another one that is a typical one that we all know. It's a cosine square of theta plus sine, this identity, sine square of theta. Actually, to make it with a double angle, to this one, that's equals to 1. And let me move this one from here because I'm going to need this space through here. There you go. Now, using these trigonometrical identities, let me write down this one, u, v. Let me just differentiate this stuff here so it doesn't get confused in the clutter. Here, using identities, then we can transform these equations into uv. Cosine, then cosine square of theta minus sine square of theta, that's equal to cosine of 2 times the angle. So that is, I can write this old formula, and then already I know that this part here equals to this product second moment of area. I know that this part here equals to xx, the moment of inertia, or second moment of area around the x-axis. And this one here is equivalent to this one here, as we know the definition we have written before. So transforming all of this, and this is going to be equal to what? Well, it's going to be xy cosine of 2 theta plus, then this one here, sine of theta times cosine of theta is sine of 2 theta divided by 2. So we're going to have this 1/2 of the difference of these two second moments of area times sine of 2 theta. Now, having that, I could define, well, what happens if I make that equal to 0? So that would tell me how angles and moments of inertia, products of inertia, or second moment of area, or product second moment of area are related to each other. Meaning, if I can find that angle theta, that would tell me the orientation with respect to the x and y coordinate system on how this other axis, or the principal set of axes, is, let's say, oriented. So if I make this equal to 0, to find the orientation of the, let me write it down, to find the orientation of principal axis, that would lead to what? Well, it would say that 0 equals to the same thing we had, the upper part, what we have written already, 1/2 of this sine of. So as I am interested in the angle, so let's try to isolate that angle theta. So I can move one part to the other. So for example, I can move this one to this part and then put anything on the bottom. So this is going to be equal to what? You can try that, the tangent of 2 times the angle. It's going to be equal to what? Well, it's going to be equal to this one here, the product second moment of area, divided by these ones here, minus here because of the change I did. Or I could rearrange it better and say, well, you know what? The tangent of this angle equals to what? 2. I'm missing a 2 here because this 2 was on the 2 times this one here. As I'm removing the negative, I can, put it in the bottom, and that would give me this order. And this is the orientation, or this is the direction of the principal axis. Direction of principal axis. Perfect. We're getting close. Any questions? What questions do you have? Perfect. Well, we found that direction. So if we are able to have such application like these ones here, and I know, because catalogs, for example, from manufacturers for U channels or T profiles, they give you the moments of inertia typically around this most common axes, for example, in this case and in this case. For the unsymmetrical sections also, you're going to find that manufacturers give you the moments of inertia around these axes that you have here, these two axes that you are here, but they are not the principal axis. Yeah, so that's why this method is convenient, because you're working from something you know, something that is given to you by the manufacturers, and you're trying to find what are the principal axes, so you can apply the simple bending theory, and then after that you find what are the neutral axes, where is the neutral axis or direction or orientation, to find how the deflation is going to go. But it means that, okay, I found this one here, but if I wanted to calculate the stress, I need to find also the moment of inertia around the u and the v axis. So meaning that I have to calculate it by using the same procedure that I used to calculate the product second moment of area here. So that is that, okay, now I need to find that, where would be convenient, here. Okay, how much is this EU and how much are EUV? Well, this one here. Well, I know that, for example, this one equals to what? Well, it's equal to this the same formula we've been using, and I know the value of V represented in terms of X and Y. So what's that? So that's what, those are the ones represented here. Actually, should I bring them, maybe to have them as a reference? This one here, and then I can paste them in here, just to have them as a reference. Equals to what? So is the integral of V squared. V is this one down here, so it's going to be Y cosine of theta minus X sine of theta square times dA. We can solve this notable product. This is binomial, and let's do it. So it's going to be equal to what? To, let's say, can I do it right away? No, let's solve it first like this. We're going to have Y squared cosine square of theta minus 2 times X, Y sine theta cosine of theta plus X squared sine square of theta, and this is multiplied by this one here, dA. Now I can split that into 3 different integrals. For example, the first one, I can take for example, this cosine square of theta, because that doesn't do anything in the integral. So this is called like this. Now you start seeing some familiar terms appearing. Now in the second one, I can write this like this like this, 2 sine theta cosine of theta integral of X and Y, another familiar term, plus sine of square of theta X squared, another familiar term. Now, if I substitute those familiar terms that are written like this into the nomenclature we have been using, so this is going to be equal to what? Well, to this one here, this one here, or to is Y. And what else? Plus this one here. You can write it like this. Sorry. You see this one here, sine. Need to move it a little bit further. Oh, it's not allow me to move this one. Let me see if I can move it enough to write down this one here, cosine of theta. Then something interesting is that I can start, for example, substituting things. I know that this one here, for example, is very close to, well, is this one here. And if I substitute just that one for the sake of clarity, I can have something like this, cosine square of theta minus xy sine of 2 theta plus yy sine square of theta. Okay, this is one step in, one bench, well, one mark. I should keep bringing down these ones here. So let's now do the same, and let's substitute those cosine square of the angle and sine square of the angle with respective trigonometric identities to transform that into a simpler value, or simple value like cosine of 2 times the angle or sine 2 times of the angle, and that's going to be something like this. So cosine of 2 times of square of the angle, I could just replace it by this one here, this one that I'm circling here. So it's going to be equal to what? It's going to be equal to so if I know that cosine of 2 angle equals to 2 times cosine square of the angle minus 1, then it means that cosine square of the angle equals to what? Well, it's going to be cosine, or 1 plus cosine of 2 times the angle, and this is going to be divided by 2. So I can write that down here, and this is going to be 1/2 of 1 plus cosine of twice the angle times this second moment of area. Now, who is going to be sine, or this sine square of theta? Well, I know that sine square of theta, I can work it out also with the cosine. So I know that the cosine of twice the angle equals to 1 minus 2 times the sine square of theta. Then it means that the sine square of theta, it's going to be what? It's going to be 1 minus the cosine of this one here divided by 2. So I could write this one here, the other one kind of in the back, plus 1/2 of 1 minus cosine of twice the angle times this one here, this moment of inertia or second moment of area. And then I have also this sine of twice the angle. And one thing that I could do there is say, okay, I remember that in the top, I got this equation here, yeah? So I could actually say that, let me write this mark here, or I want to bring this one here. Bring it back here. And I can say that, because I want to get rid of that product of inertia, so I can say that that one is equal to what? Well, it's equal to, I'll put this one to top and then divided by 2. So it's going to be equal to this one here times the tangent twice the angle and then divided by 2. Okay? So if I substitute this one in here instead of this one, so what's going to happen is that this is going to end up being let's see, pick the right one. So let me bring the, so it's going to be this one minus 1/2, because now I have that 2 there. What? It's going to have the tangent, but the tangent is defined as the sine of twice the angle divided by the cosine of twice the angle, then multiplied by this, by this one here. I'm working here. So it's going to be what? It's going to be sine square of the angle divided by cosine, just cosine of the angle, times this, I want to write smaller here, y minus x. I want to go over. Should move that to another place. But good. Okay, I can keep working on this, because the idea is to find the value of that, to maybe write a bit before here. I'm going to work with this last term, so I'm going to keep the same as before here. Try to write smaller, cosine of twice the angle, plus 1/2 y, yeah, minus what? Okay, something interesting is that, sorry, this is not angle, this is twice the angle, twice the angle. Something that we said here is that, for example, the sine square of the angle equals to 1 minus cosine square of the angle. So I can write that down here. to say, well, this equals blue 1/2 of what? Let me open parentheses here, like this, and say, well, this sine square of the twice the angle, it can be written as summation 1 minus cosine square twice the angle, then divided by what? By cosine of twice the angle, the double angle, times kind of these terms in the end. Then close parentheses. Now let's keep dividing this stuff. So it means that I could, let's say, if I multiply things here, try to divide stuff, then try to make a wall here. So, for example, the first terms here, I can turn it like, should it be nice to do it now? No, let's do it later. So let's keep writing this one in this fashion. This plus 1/2 of this one here. Then what I'm going to do here is I'm going to, this upper part, this numerator, I'm going to divide it by this denominator here and then multiply by this term in parentheses. So this is going to be end up doing like 1/2 of 1 divided by cosine of the double angle. So it's going to be second of this one times this subtraction here. Then I'm going to have plus 1/2. This divided by this one is going to be cosine of twice the angle minus this one here. And still we don't have anything useful. Well, it's partially useful because previously we managed to find what's the orientation or the direction of the principal axis. Now we're trying to find what are the values of those second moments of area in that Cartesian coordinate system formed by the principal axis. So I can calculate the stresses. Yeah. Okay, I have those. Then I can start pulling terms out of the parentheses here. For example, this one times this one times this one. I'm going to have 1/2 of this one here, plus 1/2 of this one here, plus 1/2 of this one here, minus 1/2 of cosine of twice the angle, this one here, minus, again, we repeat this end of the equation, trying to make it fit, plus 1/2 cosine of twice the angle, and then this one here. Now I can see right away that, for example, there are a couple of things. For example, this term here and this term here, I could join them. So they're going to be 1/2 of plus this one here. So this is just ordering things. And then these two components, I could write them down as 1/2 of cosine, or like this. Cosine of twice the angle. And again, it's a little bit tedious, but it is worth it, and you're going to see why. Then we have this one here, plus 1/2 of this one here, x. And what you can see right now is that there are a couple of terms that are repeating. For example, you have this term here and this term here. So the only thing is that the signs are inverted because of the internal arrangement of the parentheses. But if I just swap the terms in the parentheses, then I have to put a minus in the other side, which means that these two elements can be canceled out, ending up with this one here. That EU, or the moment of inertia about the U axis, is what? Is 1/2 of this term here minus this term here. But if I swap these two terms, then I could write them down like this. Just to keep the same order. Then we found how much is the value of the second moment of area around the U axis, which is the principal axis, by using known terms like moment of inertia around the Y and X axis. And we have just got rid of the product of inertia of the product second moment of area. Let me mark it down like with some sort of indication that, okay, this is fine. If you do the same with the let's say with the second moment of inertia around the V axis, you're going to find a pretty similar formula, because you're going to start by saying, you know what? Well, actually, let me write it in a different color. Nope, went too far away. Just let me go back. this one. V, it's going to be what? Well, it's going to be equal to this one here. Let me see. It's going to have a pretty similar structure, but instead of a plus, it's going to have a minus. So it's pretty easy to remember in that sense. And second of twice the angle. And let me mark it down also. Just by performing the same procedure as this one here. Yeah, where we know what's the value of u, because we know well that this is equivalent to what? Well, you know that this is equivalent to this one here, u squared dA. So you can get to that definition. It's pretty similar. The only difference is this one. Now, what happens if you sum these two equations here? So if you perform this sum, like how much is red to make it not that everybody notices. If you sum this term plus this term, I mean sum this one and this one, which is equivalent to summing this one and this one, what you're going to get is that this is going to be equal to, and you can easily see, to this one here. It means that there is some sort of balance between the second moments of area or moments of inertia that you're calculating, the ones that are given to you and the ones that are associated with the principal axis. So this is amazing because this last equation, this one here, can save you a lot of time. Put like this and then mark it in maybe red. This is important. And then the crucial thing comes now, because this is something that we are going to try to check. For example, let me see one equation like here. EU. Yeah, maybe this one here. Let me mark it down and try to look for that one. Shape. Yeah. So if you look at that equation, actually it's pretty kind of, it's not that it's easy, but it's, I should bring it down. This. The beauty of this is that when looking at this equation, I'm going to clean it up a little bit. So this one and this one here. And let me arrange it better, actually. So I'm going to write it down like EU. So x's are, x and y's are first. Of theta plus. Here soon is coming the usable part. And then you have this one here minus sine square of twice the angle. This equation that you have there, yeah, it is something that we could convert to this equation here. I'm going to kind of repeat the first two steps, but just to let you know what we're getting at. So if I substitute this cosine of square of the angle, as we did like here, in this part here, so that's going to be 1/2 of this one here. Plus sine square of the angle, like we did for this one here. And I leave the other term as is. Where was it? Sorry, this was not square. According to the formula here. This formula, what you're seeing right now, is pretty similar to a formula that you already have seen before, which is the formula for principal stresses. The principal stresses, I'm going to call it like that, in 2D is represented by this equation right here. And why I'm writing this down? Because if I multiply, for example, 1/2 of this times this and do the whole, let's say, multiplication between these two terms, I'm going to find, like you have here the same two values. It's going to be pretty much the similar thing. And this is equal. And this is going to be plus 1/2 of sigma x minus sigma y plus the shear stress sine of 2. So you're going to find these two equations, and these are similar. So just do the multiplication, kind of get rid of these parentheses, and you're going to find that they are exactly the same. So what that means, it means that it might be possible that we could use the same techniques when dealing with stress tensor to find out what are the principal stresses from a loading case. So let's remember that when we're talking about stress tensors, or in this case, stress element. So if I had this case that, well, I know that according to my loading case, I'm going to have such, for example, I'm going to have this sigma x. I'm going to have this sigma y, and then I'm going to have on the top, for example, these shear stresses, tau xy, and then this one here also, tau xy. And that thing was going to, this arrangement was going to give me a matrix like this one here. This is the simplification in 2D. But this was just the loading case as presented in the selected coordinate reference system, which is not the one telling me what are the largest stresses in the element, because I would have to get some sort of orientation of this thing here that would allow me to tell, or that would tell me, hey, you know what? These are the principal stresses. See? So it's principal stress 1, for example, and this is going to be principal stress 2. And look at the similitude that principal stress 2. Let me just modify this a little bit so to make it more like this. Yeah. We move this one also to here, and then we select this one, and let's remove this. Then our mission in that chapter, now I'm simplifying the case because this is a 2D representation, was to find this angle, to find the principal stresses, and then taking those principal stresses to the failure theory of our choice, or of our selection or convenience, and then do that. Now, this is pretty similar, meaning that we are given certain second moments of area along axes that are just chosen, but that they are not the principal axis. So it means that I could use the same techniques that I used for this case, to find my principal axis if I wanted to. So of course I already have the formulas for principal axis, the moment of inertia around the principal axis. I have this beautiful balancing equation of both terms, but also means that I could use, for example, Mohr's circle to calculate from one point to another these two things, or kind of the principal axis from the axis I'm given in the obligation. And let's bring it. So let me write down actually using Mohr's circle to determine we can determine a couple of things. So we could determine the second moments of area around principal axis. And it could help us, well, already define where the orientation of this principal axis, because I already have a formula for that. But let's do the Mohr circle, or use the Mohr circle for this purpose. So I'm going to bring a Cartesian coordinate system, and on the way to use the Mohr circle to determine the value of those inertia properties in the principal axis system, or Cartesian coordinate system formed by the principal axis, is saying, okay, this is something that this is going to represent in here your second moments of area, or moments of inertia, both and this one is going to represent your product of inertia, xy. So it means that, well, if you're given one pair or this triad, this one here, because you know them, they are given to you in the manufacturing process, because most of the structures we're going to be dealing with are, using beams or profiles, are structures that are formed by kind of rectangular sections, combination of rectangular sections. So you see, these are the most common, so rectangle here, and so on. So this is pretty convenient, because what you need to do in this case, to use a Mohr circle to calculate the inertia properties, but now oriented on a Cartesian coordinate system, that is oriented along the principal axis. Well, you're going to get one point, and that point, you're going to work with 2 points. The first point is going to be the pair formed by this one here. Let me write it better. And the second one is going to be formed by this pair here. So the first point is going to be something like this. So you're going to get the first point, and then you're going to plot it like, for example, here. Something can be like in here. So this is going to be this x. Then your second point is going to be something like, I don't know, in here. Comma, this one here. Let me complete this Cartesian coordinate system, because it's looking like there are missing parts in here, and this one in here, like this. Let me clean it a little bit to show that these are the negative axes. Now, first thing to do is to draw a line from one point to another. Well, the second thing, because the first thing was to put the points there. Now, this one here shows somehow the representation of the, actually this is a little bit more, let me draw it better, so it doesn't look so distorted. So, because I'm not using any scales, but so this is, for example, the reason I'm making this change, because this height here is ixy. So I should keep this height of 3, meaning that this should come to this part here. Yeah, so in here, because now this is a height of 3. Of this term here, but negative. And so put the points, and the points here are this one, negative this one. Then this cut with the horizontal axis is going to be the center of the Mohr circle. So meaning that I could draw a circle using this as a circumference, something like this. Nope. I don't want an ellipse, I want a circle. Let's see how it goes. Yeah, more or less. There you go. And it means I need to stand a little bit this one here, like this, and then delete this a little bit. And that what means that where the circle cuts the horizontal axis, that's going to mark the value of the principal axis, the second moment of area of the principal axis. Then I'm going to have, for example, from here down here, this is going to be a u, so the moment of inertia around that axis, or the second moment of area around that axis. And then in the other part, in here, just a tiny bit there, not there, I'm going to have the value of this one here. Well, so it means that you could get the values of those elements by using this graphical tool if you wanted to. So imagine how convenient is that you could use same concepts that you have used before to create those. Now, one interesting point to mention is that, let me draw another Cartesian coordinate system here, that this might be, well, these are your x and y axes. You have a way to calculate the direction of the other Cartesian coordinate system. For example, I'm going to just write it inverted just for the demonstration purposes. For example, you can find that the angle is something like this, calling this V, and then you have, this is U. I don't know why this is U. This is the angle theta, because you can calculate it now. But it might be possible that you don't know, no, bad line, has to be this one, the orientation of the neutral axis. And then why is important again the neutral axis? Well, because deformations are going to happen around the neutral axis. So you need to know what is the neutral axis, the direction or orientation, if you want to know how that thing is going to deform. So you need to know that. It might be different. And that is usually represented, well, that's going to have an angle alpha with respect to certain other axes. Yeah, but that's something to keep in mind. So we haven't yet finished something. Well, yeah, we have finished it because, well, in the sense that, you know what? Stress as formed in the beginning here is totally fine what we have done here. So now we have all the tools to calculate this stress. So because we know how to find the components of one moment in terms of the other moments, if I know the orientation, and I can know the orientation because I have the formula, and the formula is given by this one here. Where are you? This one here. So we have the orientation there. And let me bring it down because let's put all the formulas together. So now the orientation, knowing the orientation, I can then decompose the moment applied to it, or the forces applied to it. And then I know already have tools to calculate this one. And this is V and U are by inspection, meaning what are the distances that I would need to follow to find where is the largest distance to a certain point. Yeah, because for example, let's bring an L-shaped figure, for example. So I have an L-shaped figure, could be something like this, and then I bring it down like this, like this. Like this. Again, the typical axes that are given to me by manufacturers trying to find the figure, this one here. Oh no, I believe it's better this one here. Let me see. It's something like this. Yeah, this is the X and Y that is given to me by the manufacturer. And this one here, let me just rotate it a little bit. It kind of looks a little disturbing to the eye. There. Let me fix this one here also. Yeah. So you have those two, but then you know where the other axes can be, meaning that the principal axes are maybe located something like this. Let's put it like this, yeah. And then this other one, perpendicular to it. These are U and V, and an angle theta that you already know how to calculate it because of this equation here. Yeah. Then you know how to decompose stuff. For example, if you have a force applied like this in this direction, so if this is a force, then this is force in Y, but then you can decompose this in force U and a force V, and then those forces are going to create moments around those axes, and then that would allow you to calculate the stresses there. But then the point is that, hey, but you know what? I don't know how the neutral axis is, because regardless how the principal axes are, man, and this always keeps getting in the middle. This one here. Just a tiny bit like this, and then put this one. So this one here is the neutral axis, which I don't know how it's oriented, because it might not be coincident with the principal axis. And again, no matter how loads you put there, deformation is going to happen somewhere around this axis. So you need to know it. You need to know that. And well, how to get to know that? Well, that's an interesting question, because now we are stepping into how deformation is handled here, because now we know how stress is handled, but we don't know how the deformation is handled. So to get to know how much is that angle alpha, So we need to look at the problem from a different perspective, yeah? So it's kind of finding a different, let's say, way of doing things. So let's imagine that we have this type of beam, but it is a black here, and then it is a case where I have a cantilever beam. I put at the same level. Yeah? Then this is something like comes like this. Then we have, this is a cantilever beam. We have a force applied here. And this is my coordinate reference system, is something like this. Where this is Z and this is Y. And this is the section, and then if I draw a small section here, so the section is going to be something like this. Kind of draw how the section is going to be. This one here. So this is an L shape. I should have drawn it kind of in 3D, but okay. I lost the mouth for a second. Something like this. So the deformation of it, for example, if it's a cantilever beam, you can search on the tables. No, this is a typical case. So we know that the deformation of a cantilever beam is something that's going to happen. For example, it's going to be measured like, again, I'm losing the pointer of the tablet here. Got it again. So the deformation of a cantilever beam is defined by kind of the force times the length of the beam, power of 3, divided by 3 times E times I. And this is a formula. But now, deformation is going to happen across, kind of around this principal axis. Yeah. So you need to kind of, separate or consider that this deformation is going to happen differently around this principal axis, meaning that deformation in, for example, in kind of along the axis, this U axis, is going to be well, the force kind of composing U times L3 divided by this 3EIU, and the deformation happening because of this force that is not oriented kind of parallel to the principal axis is going to be force VL3 then 3EIV, meaning that if you want to calculate now the total deformation of this is going to be equal to what? To this one here plus this one here. And this is nice because now you have a way to calculate the deformation. If you want to know how really is oriented between, let's say, with respect to what's the value of that angle alpha to determine the orientation of the neutral axis, because let's remember that these things are going to happen around the neutral axis. This deformation is going to happen around the neutral axis. Then there are other ways to get to that part, definitely. And one of the ways to do it is by considering, let me draw something that's called an alternative method to calculate the stresses when the forces and moments are not aligned with the principal axis. I'm going to write it like this, like alternative method. You can use it also. Let me bring back this one. And I'm going to draw it like, oh. Is that let's consider again, a three-dimensional Cartesian coordinate system. I'm going to draw it like this. Came in red. I want it in purple. Something like this. Z-axis, like this. Then I have a generic sort of general body here, section, sorry. In that general section, again, we have a small differential of area. And on that area, there is a force applied to it. As you know, it might be a force applied to your element. And that force, we're going to consider it parallel to the z-axis. z, x, y. And let's assume also that there are a couple of moments applied to this. We're going to have some sort of a moment like this, moment y, then one moment in, and like this, moment x. And this moment is caused by this force. Let me try this better, draw this better, because this is not making any sense. So this moment would be something like this. And that moment over there is going to be contrary to this one if I say that that's the force causing the moment. Yeah. And I also know that there is a distance between the centroid of the area here. This is going to be a distance x, and there's going to be a distance y. Perfect. Now, this alternative method considers that first, the stresses caused at a certain point in the section or measure with respect to the Cartesian coordinate system xy is going to be equal to something multiplied to the distance x plus something multiplied to the distance y. So two constants. Yeah. And we're going to consider also that the force is caused by what? By this stress causing the element times the differential of area. This is a definition we know. Yeah. And again, that the force is parallel to the z-axis. Or let me write it better. It's not equal, so parallel to z-axis. Great. So if I see, or take a look at the moment around x, yeah, that moment around x is going to be caused by the force times the distance y, isn't it? So we're going to have the force, sigma dA, times y. But I know that sigma, stress, is defined as a sum of two things. And that sum of two things, so meaning that I could put this equation or assumption that I have made into here and say, well, you know what? This is going to be equal to what? Well, it's going to be equal to px plus qy times y, the derivative of the area. If I separate these two things, I'm going to say, well, you know what? This first times the second, and putting things out that, it's going to be something like this. PA plus Q y square PA, which I could write something like this. Q, this one here is IXX, moment of inertia around the x-axis. Just remember the definition of things. So the moment in x, or around x, is going to be equal to what? To that thing that we have just derived. Now, for the moment in y, I'm going to have that. Why is that? Well, it's going to be kind of contrary to in the other direction. So it's going to be kind of the force caused by the moment, the force times the x distance is going to cause negative moments, as we have understood how negative moments are, which are not following the right-hand rule. So it means that this is going to create a negative moment like this. It's a force, negative force, dA times x, and again that I can transform into using the definition we've given before. And this transform finally into minus p. When you get rid of those parentheses and transform and take those known quantities, from integrals to second definition of second moment of areas, so you're going to have something like this. Now, as I know that the neutral axis happens when in bending, when the bending stress is equal to 0, it means that I could say, well, you know what? Px times Qy equals 0. That's when the bending is, that is when it's happening. Then it means that I can change a little bit things. Where is it? That y divided by x, if I just put it in this sense, move this that's going to be equal to minus P divided by Q. Actually, if you see this can be transformed into a straight line with slope of this one times x, meaning a straight line starting from the origin of the Cartesian coordinate system and growing or decreasing at a rate dictated by the slope, which is P divided by Q. And if this is a slope, it means that the tangent, the tangent of the slope equals the angle, the orientation of that straight line with respect to the x-axis. So this tangent of this one equals to minus P divided by Q. Hence, this here, what we have just been given here, tells us the magnitude of alpha. Now you say, well, how can I calculate those P and Q? Well, you have a couple of formulas here that could help you do that. Yeah? They could help you do that. Then it means that now you have tools to calculate, let me put it in the same color. This one here. This is the orientation of the neutral axis. Neutral axis. And more interesting is that if you have the orientation of the neutral axis and you use the Mohr circle that we graphed here, and I'm going to copy it like this. So if you're facing this type of problems where you need to deal with asymmetric bending here. So now if you know that alpha, it means that you can draw the position of the neutral axis in here. Let's assume that is this one. So this is telling me 2 alpha. Remember that in the Mohr circle, the angles are doubled. So this is the neutral axis position. And if you have the neutral axis position, you can get in here the value of the second moment of area around the neutral axis. I'm going to call it, it's too small here. And if you get that value, it means that you can directly say, well, the stresses are defined by what? By the moments around the neutral axis. Why? It just covers this neutral axis times the distance or a distance from the neutral axis to the farthest away point divided by the moment of inertia with respect to the neutral axis. This is n. Who is that n? Well, n can be, for example, this can be n. And that n is measured from here to here. So you get to know how much is the stresses at this point n, or n could be, or n or m inclusive, depending on where you want to have it. Those are the farthest away point from the neutral axis. There you go. Then either on m or n, then you can substitute those ones here, and you will get the value of the stresses that you're looking for, or m. I would say this is a pretty nice way of doing this stuff. So let's summarize this stuff. Any questions so far? We started by saying that the way to deal with bending is using the simple bending theory, Euler-Bernoulli theory, that is represented here. And we define that bending or symmetric bending is that one that happens kind of in the plane of symmetry, when the bending occurs in the plane of symmetry. Yeah. That plane of symmetry for symmetric figures are coincident with principal axis. Yeah. And that's something that is nice, but when you don't have symmetrical sections, then those typically given reference axes are not aligned with the principal axis. And the reason for that is that commercially, or structurally, when we go in practice, these are the typical axes. For example, this one here and this one here are the typical axes that you use, for example, for L-shaped beams or Z-shaped beams. But no, these are the ones that you use for construction purposes to align your stuff. But those are not your principal axes or principal axis of symmetry. And the good thing is that for any shape, for more weird shaped that you can have there is always going to be a position where you're going to find that the product second moment of area is going to be equal to 0, meaning that you're going to end up with maximums and minimums second moments of area that represents at that position the principal axis. So our task is to find out how much are they, because that's going to help us to calculate the stresses. So for simple cases, for example, where there is a moment or a force not aligned with the axis of symmetry, then you could decompose that force with the axis of symmetry, and then you could calculate the stresses in this fashion here. But however, if you don't have that right away, then you need to find the orientation of the principal axis to find the values of the second moment of area around those principal axes, which is the term I use interchangeably with a moment of inertia. They represent the same, and then you'll find the values of those moments there. So to do that, we started from the premise that we had a section and we have the XY Cartesian coordinate system typically given to us, but we knew that the principal axes are oriented differently because we're talking about an unsymmetric bending. And then we started deriving, for example, what were the values of the product second moment of area in the principal axis. We're taking from the point of view of the XY axis here. So we continued all that, and the first thing we found is that we get to know, or we can know, what is the orientation of the principal axis by using those predefined values of properties in another system oriented differently, like this one here. Doing the same type of procedure, we could find what are the values of the second moment of areas around both U and V axis, which represent the principal axis. We also found this nice balance, meaning that if you have moments of inertia around X and Y, and then you find the moment of inertia around U, then you get to find the fourth one because there is a balance between the four of them. Now we said that these equations that we found are pretty similar to the ones found in the state of stress concept, where we have a loading case that causes certain stresses, but those stresses might not be the maximum because maximum stresses are oriented differently. Where the shear stresses are 0, then that similitude allows us to use, for example, Mohr circle to determine the value of if we wanted to use this graphical tool, for example, without using any formulas, we can find the values of the moments of inertia around the U and V axis by using just this graphical tool, or even you can use those tools already available on the internet that you can graph the Mohr circle, but instead of giving the normal stresses X and Y and the shear stress, you give the moment of inertia in X, moment of inertia in Y, and the product of inertia, and they will give you the values of the moments of inertia in the principal axis, like is shown here. So we talked about that, and then after having defined them, now we have a way to calculate the stresses of that loading case. Then we said, well, if you wanted to calculate the deformation, you could use any means that we have used before. But if this is a typical case, that you can use a tabulated equation like a cantilever beam, like we're showing here for an L-shaped section, then you can say, well, I would need to decompose, for example, the forces, now knowing how the orientation of the principal axis are. So that force F, I need to decompose it into the U and V axis, and then calculate the deformation of each one of those, add it as a vector sum here, and then take the magnitude. And then I can say how much is the deformation of it. Yeah, but it's not enough, because you would like to know how much is the neutral axis, because remember that the stresses, neutral axis is where stresses are 0, and it means that that's the point of reference that you're going to use to measure what are the maximum stresses at a certain farther away point from that neutral axis. And then you need to know what that neutral axis, or how is it oriented. And then we went into this alternative method to calculate stresses by considering that they are the sum of two things. But then at the end, we found out that, oh, you know what? And by using this method, then we get to know what's the orientation of the neutral axis. And then having the orientation of the neutral axis, for example, is kind of written here. I could come back to the Mohr circle and draw that line represented the neutral axis. But just remember that, if the angle with respect to of the neutral axis with respect to x is alpha, in the Mohr circle is going to be 2 alpha, because it's twice the angle in the Mohr circle scenario. Then whatever the neutral axis, let me write it down here, cuts the Mohr circle, I come down here, and that's going to give me the inertia around that neutral axis. And then if I have the inertia around that neutral axis, I can calculate the stresses, because now I have all the ingredients possible to do it easily, just by saying, you know what, stresses at any point N or M can be calculated from the neutral axis data by using this formula here. Of course, the only thing is that you have to find the moments now around the neutral axis. and now you can deal practically with unsymmetric bending. What questions do you have? Great, none questions. If no, then I would like you to wish a nice weekend, and I'll see you next week with another topic. I believe it's going to be sine valence equation for torsion, and it's a very interesting topic also that has a very practical application. So have a very nice week, and well, end of the week and next week also, and take care. Bye.